Good morning, everyone. I am Sherry Ann Sakarias, Assistant Professor in the Department of Electronics and Communication at Rajagiri School of Engineering and Technology. Today, I will be discussing on an introduction to microwaves and waveguides. This is a topic that comes under the course Microwave and Radar Engineering for S7 EC students. The topics of this presentation are as follows. We will start with an introduction to the subject. Then we will discuss on the advantages and applications of microwaves. We will then move on to discuss what are waveguides. Then we will have a review on the basic concepts of electromagnetic wave theory. We will then discuss on the propagation of waves in a rectangular waveguide and derive an expression for the cutoff frequency of a rectangular waveguide. We will then move on to discuss on what are cavity resonators and the expression for resonance frequency for a rectangular cavity resonator. The reference textbooks are Microwave Devices and Circuits by Samuel Liao and Microwave Radar Engineering by Kulkarni. Now, what are microwaves? Microwaves are defined as the region of the electromagnetic spectrum in the frequency range from 300 MHz to 300 GHz. The corresponding wavelength of microwaves is in the range of 100 centimeters to 0.1 centimeters. So this table over here shows the various IEEE frequency bands. So you can see the microwave frequency range from 0.3 gigahertz to 300 gigahertz. So the commonly used microwave frequency bands are the L band, which is from 1 to 2 gigahertz, the S band, which is from 2 to 4 gigahertz, the C band, which is from 4 to 8 gigahertz, the X band, which is from 8 to 12 gigahertz. Most of the devices in the microwave labs are in the X band. Similarly, you have the Ku band, which is from 12 to 18 gigahertz, the K band, which is 18 to 27 gigahertz, and the Ka band, which is from 27 to 40 gigahertz. Now, all the frequencies above 40 gigahertz are known as the millimeter waves. Now, we know that the spectrum up to 30 gigahertz is highly congested and used up. So, the millimeter waves is considered as the solution in the next generation of wireless communication or 5G. So, as you go to higher frequencies, the size of the antenna that can be used become smaller. At the same time, the data rates can be much higher, so you can have data rates of up to 10 gigabits per second in the millimeter waves. The advantage of microwaves are as follows. As you increase the frequency, you have higher bandwidth or transmission rates possible. That is, it can carry a large amount of information and you can use it for point-to-point communication. Now, as the frequency increases, we know the wavelength decreases and the size of the antenna is proportional to the wavelength. So you can have antennas of smaller size. The third advantage is that you have improved gain and directive properties. The reason is that again gain and directivity are inversely proportional to wavelength. So for microwaves the wavelength is small, which means you have improved gain and directivity. Similarly, the effects of noise and fading are minimum due to the use of line of sight propagation techniques. So the amount of reflections will be minimum. And another advantage is that the power required for the transmission of microwaves is much less when you compare it to a low frequency signal. Another advantage of microwaves is that it is transparent, or it can easily pass through the ionosphere, which thus it can be used for space as well as satellite communication. So you require only a few number of repeaters. The applications of microwave is that it can be used in telecommunication, radar. It can be used in commercial industrial applications which involve microwave devices and components. Then it can also be used in biomedical applications and electronic warfare. Now, what are waveguides? A waveguide is a hollow metallic structure that has a uniform cross-section throughout. The main function of a waveguide is that it is used to guide electromagnetic waves from one point to another. This is done by successive reflections from the inner walls of the tube. Now, a waveguide can have different shapes like rectangular, circular, elliptical, and so on. So this figure over here shows two types of waveguides. One is a rectangular waveguide which has a rectangular cross section, and the other is a circular waveguide in which the cross section is circular. This table shows the differences between a transmission line and a waveguide. So a transmission line, you know that it supports only a transverse electromagnetic wave. That is, a transverse electromagnetic wave means both the electric and magnetic fields are perpendicular to the direction of propagation of the wave. Whereas in a waveguide is able to support transverse electric, transverse magnetic, as well as a TEM wave. Now, transmission lines are used at lower frequencies. That is, what happens at higher frequencies is that the transmission line becomes inefficient due to the skin effect and dielectric losses. Waveguide is a structure that can be used at the microwave range frequencies and can be used to obtain a larger bandwidth with a lower signal attenuation. Transmission lines generally operate from DC to a high frequency. That is, it acts similar to a low pass filter, whereas a waveguide will operate only above a certain frequency known as the cutoff frequency. So this acts similar to a high pass filter. A waveguide cannot transmit DC or lower frequencies. The reason is that at lower frequencies, the dimensions of the waveguide become too large. Now we will look into the structure of a rectangular waveguide. So it's basically a hollow metallic structure such as copper can be used as the waveguide, and here you can see that the cross section is rectangular in shape. The inner surface of the waveguide is coated with a thin lining of materials such as gold or silver. This is done to improve the conductivity and minimize the losses as the wave propagates. The waveguide is filled with a dielectric medium such as air, and here you can see the dimensions of the waveguide along the x and y directions are given, and here we can assume that the wave is propagating in the z direction. Now, in order to analyze the propagation of waves in a waveguide, we will first have a quick review of the basic concepts of electromagnetic wave theory. So we will start with the Maxwell's equations. So here E and H stand for the electric and magnetic field vectors. D stands for the electric flux density and B stands for the magnetic flux density. So D is defined as epsilon into E, where epsilon is the permittivity of the medium, and B is defined as mu into H, where mu stands for the permeability of the medium. So the first Maxwell equation is del cross H is equal to J plus dou D by dou T. This is also known as the modified form of Ampere's law. This states that a time varying electric field will produce a magnetic field. The second equation is del cross E is equal to minus dou B by dou T. This is also known as Faraday's law. This states that a time varying magnetic field will produce an electric field. The third equation is del dot D is equal to rho. This is also known as Gauss law, and this states that the electric flux across a closed surface is proportional to the charge enclosed. And the fourth equation is del dot B is equal to 0. This is the Gauss's law for magnetostatics, which states that the magnetic flux across a closed surface is 0. Now from the basic Maxwell equations, we will now derive the wave equations. So we will start with the field vectors. So we know that the field vectors are varying in a sinusoidal manner with respect to time. So I can assume that the electric field E can be defined as E0 e raised to j omega t, where E0 stands for the maximum value of the electric field intensity and omega is the angular frequency, which is defined as 2 pi f. So now if you differentiate this equation with respect to t, we'll get dou E by dou t is equal to E0 j omega e raised to j omega t, or you can write this as j omega times E. Okay, so now we can define an operator dou by dou t is equal to j omega. So if we try to differentiate this equation once again with respect to t, we will get dou square E by dou t square is equal to E naught into j omega the whole square e raised to j omega t. Okay, so this, we know that j square is equal to minus 1. So this you can also write it as minus omega square into E. So from this equation, you can define another operator dou square by dou t square is equal to minus omega square. Okay, so I'm going to write this as equation 1 and this as equation 2. Okay, now I'm going to assume or consider a medium which does not contain any free charge carriers and is non-conducting in nature. Okay, so for example, air or free space. Okay, so if the medium does not have any charge carriers, you can say rho is equal to 0, and if it is non-conducting in nature, you can say that sigma is equal to 0. Okay, so now we know that the current density J is equal to sigma times E, which will be equal to 0. So now Maxwell's equations can be rewritten. So we know that del cross H is equal to J plus dou D by dou T. Okay, where now because the medium is non-conducting and free of charge carriers, J term is 0. Okay, so this becomes equal to dou D by dou T. Okay, so now what is D? D is the electric flux density, which is given by epsilon times E. Okay, so since epsilon is a constant, I can take it out. So this is equal to epsilon dou E by dou T. Okay, so now we have already defined the operator dou by dou T is equal to j omega. So you can write this as del cross H is equal to j omega epsilon E. Okay, so this is an important equation. So I'm going to mark this as equation 3. In the similar way, we know that according to Maxwell's equations, del cross E is equal to minus dou B by dou T, where what is B? B is magnetic flux density, which is defined as mu into H. Since mu is the permeability of the medium, is a constant, you can take it out. So you can write this as minus mu dou H by dou T. Okay, again we know that the operator dou by dou T is equal to j omega. So we get an expression as del cross E is equal to minus j omega mu into H. Okay, and so you can put this in a box and this will be our equation number 4. Now on taking the curl of equation 4, we get del cross E is equal to del cross of minus j omega mu into H. Now from vector analysis, we know that del cross E is the same as del of del dot E minus del square E, where del square is the Laplacian operator. So this is equal to minus j omega mu into del cross H. Now from Maxwell's third equation, we know that del dot D is equal to rho. This is the Gauss's law. Now D is the electric flux density, which is the same as epsilon into E, and rho is the charge density. Now we have assumed that the medium is free of charge carriers, which means rho is equal to 0. So we get epsilon into del dot E is equal to 0. Now we know that epsilon is the permittivity of the medium, so that cannot be 0, which means del dot E must be equal to 0. So substituting this condition in the equation 5, we will get minus del square E is equal to minus j omega mu into del cross H. Now what is del cross H? Del cross H is j omega epsilon E. Okay, so we will get minus del square E is equal to omega square mu epsilon into E. So we can write del square E is equal to minus omega square mu epsilon into E. Now resolving the electric field vector into three mutually perpendicular directions, we can write del square of I cap Ex plus j cap Ey plus k cap Ez is equal to minus omega square mu epsilon into I cap Ex plus j cap Ey plus k cap Ez, where I cap, j cap and k cap are the unit vectors along the x, y and z directions. So in general, the wave equations can be written as del square E is equal to minus omega square mu epsilon E, and del square H is equal to minus omega square mu epsilon into H. So the electric and magnetic field at any point x, y, z of an electromagnetic wave should satisfy these wave equations, which are simply second order differential equations. Now you can also rewrite the wave equations in terms of the speed of light. So here we know that mu epsilon, you can also write it as in terms of the absolute and relative permeabilities and permittivities as mu epsilon is equal to mu naught mu r into epsilon naught epsilon r. Okay, so now for air, you know that the relative permeability and permittivity is equal to 1. Okay, so this expression reduces to mu epsilon is equal to mu naught into epsilon naught, where mu naught and epsilon naught are the absolute permittivity and permeability of the medium. So this you can also write it in terms of the speed of light. So we know that c is equal to 1 by root mu naught into epsilon naught. So you can write mu epsilon is equal to 1 by c square. So by substituting this equation 8, okay, in the equations 6 and 7 and replacing this minus omega square with the operator dou square by dou t square, we will get del square E is equal to 1 by c square dou square E by dou t square, and del square H is equal to 1 by c square dou square H by dou t square. So these equations represent waves propagating through free space with a velocity equal to that of light. So these are also known as the Helmholtz wave equations. Okay, so this figure over here shows an electromagnetic wave that is propagating in the x direction, and you can see that the electric field vector and the magnetic field vector both are perpendicular to the direction of propagation of the wave. Now we will look at the propagation of waves in a rectangular waveguide. So consider a rectangular waveguide that is filled with a dielectric medium such as air. So this rectangular waveguide is being placed in a rectangular coordinate system with its breadth along the x-axis and its width along the y-axis, and the wave is assumed to be propagating along the z direction. Okay, so hence the wave equation can be written as del square Ez is equal to minus omega square mu epsilon into Ez, and del square Hz is equal to minus omega square mu epsilon into Hz. So here del square stands for the Laplacian operator. So the Laplacian operator in the rectangular coordinate system can be defined as dou square Ez by dou x square plus dou square Ez by dou y square plus dou square Ez by dou z square is equal to minus omega square mu epsilon into Ez. Now the wave is propagating in the z direction. Okay, so since the wave is propagating in the z direction, the field vector, you can write it as E is equal to E0 e raised to minus gamma z, where gamma stands for the propagation constant. Okay, so if I take the derivative of this field vector with respect to z, we will get dou by E by dou z is equal to minus gamma E0 into e raised to minus gamma z. So this E0 e raised to minus gamma z is the same as E. So you can write this as equal to minus gamma times E. Okay, so we can define another operator dou by dou z is equal to minus gamma. Okay, so I'm going to use this definition over here. So by substituting this in this particular equation, dou square by dou z square can be replaced with gamma square. Okay, so now we get an expression as dou square Ez by dou x square plus dou square Ez by dou y square plus gamma square Ez is equal to minus omega square mu epsilon into Ez. Okay, now if I take the components of the electric field along the z direction together, you will get gamma square plus omega square mu epsilon into Ez. Okay, so now this gamma square plus omega square mu epsilon, you can replace it by another term h square. Okay, so here gamma represents the propagation constant along the z direction, and this omega root mu epsilon represents the propagation constant along the structure. Okay, so you can replace this with a term h square. So the wave equations for TM and TE waves can be expressed as dou square Ez by dou x square plus dou square Ez by dou y square plus h square into Ez is equal to 0 for a TM wave, and dou square hz by dou x square plus dou square hz by dou y square plus h square hz is equal to 0 for a TE wave. Okay, so the main difference between a TE, TM and a TEM wave is that for a TE or a transverse electric wave, the electric field is transverse or perpendicular to the direction of propagation. That is, if the wave is propagating in the z direction, Ez will be equal to 0, but there will be some component of the magnetic field along the z direction. That is, Hz will not be equal to 0. Similarly, for a transverse magnetic wave or a TM wave, the magnetic field will be transverse or perpendicular to the direction of propagation. That is, Hz will be equal to 0, but Ez will not be equal to 0. And in the case of a transverse electric and magnetic wave or a TEM wave, both the electric and magnetic fields are transverse to the direction of propagation. That is, Ez will be equal to 0. At the same time, Hz will also be equal to 0. Now from the basic Maxwell equations, you can determine the components of the electric and magnetic field in the x and y direction. Okay, so in order to do that, we will start with the basic Maxwell equation, the first equation, which is del cross H is equal to j omega epsilon into E. Okay, so now I'm going to expand this del cross H in the rectangular coordinate system. So that will be determinant of I cap, j cap, k cap, dou by dou x, dou by dou y, dou by dou z, hx, hy, hz. This will be equal to j omega epsilon into, by resolving the electric field in the three mutually perpendicular directions, you will get I cap ex plus j cap ey plus k cap into Ez. Okay, so now taking the determinant and expanding, and then if you equate the I cap, j cap and k cap terms, you will get dou hz by dou y plus gamma into hy is equal to j omega epsilon ex. Dou hz by dou x plus gamma hx is equal to minus j omega epsilon ey, and dou hy by dou x minus dou hx by dou y is equal to j omega epsilon into Ez. Okay, so here what we have done is you have replaced this dou by dou z with the term gamma, okay, which is the propagation constant. So we get three sets of equations. In a similar way, on taking the second Maxwell equation, del cross E is equal to minus j omega mu into h. You can expand del cross E in the rectangular coordinate system and then equate the coefficients of I cap, j cap and k cap. So you will get another set of three equations. Dou by dou y Ez plus gamma Ey is equal to minus j omega mu Ex. Dou Ez by dou x plus gamma Ex is equal to j omega mu Hy, and dou Ey by dou x minus dou Ex by dou y is equal to minus j omega mu into Hz. Okay, so for using these set of 6 equations, you can find the component of the electric and magnetic field in the x and y directions. Okay, so for example, if you want to find the component of the electric field in the x direction, you can start with equation 5. So from equation 5, you first find an expression for Hy and then you substitute it in equation 1. So from equation 5, we can write Hy is equal to dou Ez by dou x plus gamma Ex divided by j omega mu. Okay, now substituting this expression of Hy in equation 1. So we know that equation 1 is dou Hz by dou y plus gamma Hy is equal to j omega epsilon Ex. Okay, so in this equation, if you substitute this Hy, okay, you will get dou Hz by dou y plus gamma by j omega mu into dou Ez by dou x plus gamma Ex is equal to j omega epsilon into Ex. Okay, so now what we are going to do is I'm just going to open this bracket and then I'm going to group together the Ex terms. Okay, so if I group together the Ex terms, I'll get dou Hz by dou y plus gamma by j omega mu dou Ez by dou x is equal to Ex into j omega epsilon minus gamma square by j omega mu. Okay, now on multiplying this equation 8 with j omega mu, you will get j omega mu into dou Hz by dou y plus gamma into dou Ez by dou x is equal to Ex into minus omega square epsilon mu minus gamma square. So if you take this negative sign out, you will get a term gamma square plus omega square epsilon into mu, which is nothing but h. So this is equal to minus h square into Ex. So from this equation, you can find the expression for the electric field component along the x-axis as Ex is equal to minus j omega mu by h square dou Hz by dou y minus gamma by h square dou Ez by dou x. Okay, so in this same manner, you can find the electric field component along the y direction. At the same time, you can also find the magnetic field component along the x-axis and y-axis. So that is given by equations 9 to 12. Now we will look at the propagation of TM waves in a rectangular waveguide. So we know that for a transverse magnetic wave, the magnetic field is always transverse to the direction of propagation of the wave. So if you assume that the wave is propagating in the z direction, then there will not be any component of the magnetic field along the direction of propagation of the wave. That is, Hz will be equal to 0 and Ez will not be equal to 0. So the wave equation for a TM wave is given by dou square Ez by dou x square plus dou square Ez by dou y square plus h square into Ez is equal to 0. So this is a second order partial differential equation. So we are going to use the method of separation of variables in order to get the different field components Ex, Ey, Hx and Hy. So for that, what we're going to do is I'm going to assume that the electric field component Ez is equal to x into y, where x is a pure function of small x and y is a pure function of small y. Okay, so if I substitute this value of Ez in this equation 1, we will get dou square of xy by dou x square plus dou square of xy by dou y square plus h square into xy is equal to 0. Okay, so now I told you that capital X is a pure function of small x and capital Y is a pure function of small y. So these two terms are independent. Okay, so if when I take the derivative with respect to x, y is a constant, so it can be taken out. Similarly, if I take the derivative with respect to y, x is a constant and can be taken out. Okay, so you can write this as y into dou square capital X by dou x square plus x into dou square capital Y by dou y square plus h square of xy is equal to 0. Okay, since x and y are independent variables. Now, on dividing this equation by xy, you will get 1 by x dou square capital X by dou x square plus 1 by y dou square capital Y by dou y square plus h square is equal to 0. Now we know that h is a constant. Okay, so since h is a constant and this first term over here is a pure function of x and the second term is a pure function of y, the sum of these terms is a constant, which means each of these terms is a constant separately. Okay, so you can write, since this is a pure function of x, you can write this 1 by x dou square x by dou x square is equal to some constant minus b square, and the second term 1 by y dou square y by dou y square is equal to another constant, so you can write this as minus a square. Okay, so when I substitute these equations 3 and 4 in the equation 2, this equation 2 becomes minus b square minus a square plus h square is equal to 0. Okay, or in other words, h square is equal to a square plus b square. Okay, now these equations 3 and 4, they are actually second order differential equations. Okay, so the solution of these second order differential equations can be written as capital X is equal to C1 cos bx plus C2 sin bx, and y can be written as C3 cos ay plus C4 sin ay. So here C1, C2, C3 and C4 are constants which have to be evaluated by applying the boundary conditions. So the complete solution is given by Ez is equal to xy, where x is equal to c1 cos bx plus c2 sin bx, and y is given by c3 cos ay plus c4 sin ay. Okay, so now in order to find the constants C1, C2, C3 and C4, we will evaluate the boundary conditions. So we know that since the entire surface of this rectangular waveguide acts as a short circuit or ground for the electric field, Ez will be 0 along the 4 boundary walls. Okay, so since there are 4 walls, there are 4 boundary conditions. So in the first step, I'm going to apply the boundary condition to the bottom plane. Okay, so Ez is 0 along the bottom plane. Okay, so the bottom plane can also be represented as y is equal to 0 for all x ranging from 0 to a. Okay, so Ez will be equal to 0 at y is equal to 0 for all x ranging from 0 to a. That represents the bottom plane. Okay, so if I substitute this condition in the complete solution, you will get Ez is 0 and you substitute y is equal to 0. So if you substitute y is equal to 0 in this equation 5, C3 cos 0 is 1 plus C4 sin 0, which is 0. Okay, so this term is going to get eliminated. So you will get 0 is equal to C1 cos Bx plus C2 sin Bx into C3. Okay, so since this is the product of two terms and x varies from 0 to a, so this term cannot be 0. Therefore, C3 will be equal to 0. Now since C3 is equal to 0, the solution reduces to Ez is equal to C1 cos Bx plus C2 sin Bx into C4 sin Ay, because the C3 is equal to 0. Okay. Now in the second step, I'm going to apply the boundary condition to the left side plane. Okay. So the left side plane can be represented as x is equal to 0 for all y ranging from 0 to b. That is what is written over here. Okay, so when you apply the boundary condition, Ez will be 0 at x is equal to 0 for all y ranging from 0 to b. Okay, so when I substitute this condition in the equation, what will happen is here x is equal to 0. Okay, so 0 will be equal to C1 cos 0 plus C2 sin 0. So sin 0 is 0. This becomes C1 into C4 into sin Ay. Okay, so again this is the product of two terms and y ranges from 0 to b. So this term cannot be 0. Therefore C1 will be equal to 0. Okay, so we got the next constant. Now again the solution is going to reduce to Ez is equal to C2 sin Bx into C4 sin Ay. Okay, now in the third step, I'm going to apply the boundary condition to the top plane. Okay, so how do you represent the top plane? Top plane is represented as at y is equal to b for all x ranging from 0 to a. Okay, so this plane is at y equal to b for all x ranging from 0 to a. What is the condition? Ez is equal to 0. Okay, so I'm going to substitute this condition in this equation over here. So since y is equal to b, so if you substitute y is equal to b, this becomes 0 is equal to C2 sin Bx C4 sin AB. So since x is ranging from 0 to a, here you can, this will not be 0, so you can say C4 sin AB is equal to 0. Okay, so here since if sin AB is equal to 0, it means AB must be equal to n pi, or you can write A must be equal to n pi by b. Okay, so in the last step, what I'm going to do is I'm going to apply the boundary condition to the right side plane. Okay, so in the right side plane, this is can be expressed as at x is equal to a and for y ranging from 0 to b. Okay, so Ez will be equal to 0 at x equal to a for all y ranging from 0 to b. Okay, so again if you substitute this condition, you will get 0 is equal to C2 sin BA into C4 sin AY, and here you can see that since y ranges from 0 to b, this term cannot be 0. Okay, which means sin BA must be equal to 0. So if sin BA must be equal to 0, it means BA is equal to m times pi, or B can be represented as m pi divided by A. Okay, so we found out an expression for capital A as well as capital B. Okay. Now the complete solution is given by Ez is equal to C2 C4 sin Bx into sin Ay. Now you know what is B and what is A. Okay, and the C2 into C4, since both are constants, you can replace it by a single constant C. Okay, so the solution is now given as C into sine of B is what, m pi by A x into sine ay, where a is n pi by b into y. Okay, so this is the magnitude component. Okay, so if I want to write the expression for the electric field along the z direction, I can write it as E of z comma t, which means it is a function of the direction as well as time, is equal to the magnitude component. What is the magnitude component? C sine m pi by ax into sine n pi by by into e raised to minus gamma z into e raised to plus j omega t. So here this term over here is the magnitude component. E raised to minus gamma z represents that the wave is propagating along the z direction, and e raised to plus j omega t represents that the field is varying in a sinusoidal manner with respect to t. Now we will look at the cutoff frequency of a rectangular waveguide. Okay, so we know that in a rectangular waveguide, h square is equal to gamma square plus omega square mu epsilon, where h is a constant. Okay, and we have already seen in the propagation of TM waves how this h square can be represented as a square plus b square, where what is a? A is n pi by b and b is m pi by a. Okay, so a and b are the dimensions of the waveguide. Okay, so this you can rewrite this equation in terms of gamma square as gamma square is equal to m pi by a the whole square plus n pi by b the whole square minus omega square mu epsilon. Okay, so now here gamma stands for the propagation constant. So you can write gamma is equal to, taking the square root on both sides, you get gamma is equal to root of m pi by a the whole square plus n pi by b the whole square minus omega square into mu epsilon. So here gamma represents the propagation constant. So propagation constant, you already know that propagation constant gamma is equal to alpha plus j beta, where what is alpha? Alpha is the attenuation factor and beta represents the phase constant. So at lower frequencies, this omega square mu epsilon will be much less than m pi by a the whole square plus n pi by b the whole square. So if omega square mu epsilon is less than this, it means that your propagation constant gamma will be real and positive. That is, it is equal to the attenuation constant. Okay, so that means the wave is completely attenuated and there is no phase change. Okay, so if the wave is completely attenuated, it means there is no propagation. Whereas at higher frequencies, what happens at higher frequencies? Omega square mu epsilon will be greater than m pi by a the whole square plus n pi by b the whole square. So in this case, the propagation constant gamma will become imaginary, which means there is a phase change. So if there is a phase change, it means that the wave can propagate. Now the frequency at which gamma becomes 0 is known as the cutoff frequency or the threshold frequency, which is denoted as Fc. Okay, so at f is equal to Fc, omega will be equal to 2 pi Fc. So you can write it as omega c, and gamma will be equal to 0. Okay, so you already know that gamma can be expressed as root m pi by a the whole square plus n pi by b the whole square minus omega square mu epsilon. Okay, so when gamma is equal to 0, omega you can write it as omega c. Okay, so you can get an expression for omega c as 1 by root mu epsilon into m pi by a the whole square plus n pi by b the whole square the whole raised to half. Okay, so this is omega c. So from omega c, you know that omega c is equal to 2 pi fc. So you can find an expression for the cutoff frequency fc. Therefore, the cutoff frequency fc can be expressed as 1 by 2 pi root mu epsilon into m pi by a the whole square plus n pi by b the whole square the whole raised to half. Okay, so now you already know that the speed of light c is the same as 1 by root mu epsilon. Okay, so you can replace this expression in terms of the speed of light. So you can say cutoff frequency Fc is equal to c by 2 pi into m pi by a the whole square plus n pi by b the whole square the whole raised to half. Okay, so in the same way, you can also get an expression for the cutoff wavelength, and the cutoff wavelength is simply represented as lambda c is equal to c by fc, where fc is the cutoff frequency. Okay, so this you will get an expression as lambda c is equal to 2ab divided by root m square b square plus n square into a square. So we have seen the propagation of waves in a waveguide, and we have seen how the waves will be propagated only if the frequency is greater than the cutoff frequency. Now, what is a cavity resonator? So if one end of the waveguide is being terminated using a shorting plate, there will be reflections. Okay, so if another shorting plate is placed at a distance, let's say an integer multiple of lambda by 2, the signal will travel to and fro between the two plates. Okay, this results in a resonance, and the structure is known as a cavity resonator. Okay, so now here a cavity resonator will have three dimensions, A, B as well as D. Okay, so here you can see there are two types of cavity resonators. This is a rectangular cavity resonator and this is a circular cavity resonator. Okay, and you can see that here the presence of standing waves when the distance between the shorting plates is 3 lambda g by 2. Now we will look at the expression for the resonant frequency of a rectangular cavity resonator. So we know that in a rectangular waveguide, h square is equal to gamma square plus omega square mu epsilon, that is also equal to a square plus b square, where a is n pi by b and b is m pi by a. Okay, so here you can write omega square mu epsilon is equal to m pi by a the whole square plus n pi by b the whole square minus gamma square. Here gamma stands for the propagation constant. So if a wave propagates through the waveguide, there must be a phase change. So you can say gamma must be equal to j beta. That means it must be imaginary. Okay, so here you can write omega square mu epsilon must be equal to m pi by a the whole square plus n pi by b the whole square minus gamma square, which is minus j beta the whole square, or plus beta square. So if a wave has to exist in a cavity resonator, there must be a phase change corresponding to a given guide wavelength or lambda g, where guide wavelength is the distance traveled by the wave in order to undergo a phase shift of 2 pi radian. That is, here beta must be equal to 2 pi divided by lambda g. So the condition for a cavity resonator to resonate is beta must be equal to p pi by d, where p is a constant. It can take integer values 1, 2, 3, etc. just like m and n, and d stands for the length of the resonator. So at the resonant frequency, f will be equal to f naught, omega is equal to 2 pi f naught, which is equal to omega naught, and beta is equal to p pi by d. So when you substitute this in the previous equation, you get omega naught square mu epsilon is equal to m pi by a the whole square plus n pi by b the whole square plus p pi by d the whole square. So you get an expression for omega naught. Now you know that omega naught is 2 pi f naught. Okay, so we can get an expression for f naught. Okay, now you can write the expression for f naught in terms of the speed of light, because we know that c, the speed of light, is equal to 1 by root mu epsilon. So you can get an expression for the resonant frequency f naught as c by 2 into m by a the whole square plus n by b the whole square plus p by d the whole square the whole raised to half. So here m, n and p represent the half cycle variations of the field in the X, Y and Z directions. A, B and D represent the dimensions of the rectangular cavity resonator. So to conclude, in this presentation, we discussed on an introduction to microwaves, and then we moved on to discuss on the waveguides and propagation of waves in a rectangular waveguide. We also discussed what a cavity resonator is and how to derive an expression for the resonant frequency of a rectangular cavity resonator. Thank you.